We're embarking today on a deep dive into generative AI, or IO generativa. For a long time, the promise of machine learning was really that computers would get smarter at making predictions.
Right.
Better at spotting patterns in these giant data sets than any human could ever hope to be.
Yeah.
But we've kind of moved past that now.
We absolutely have. The fundamental shift we're looking at today is it's this leap from just prediction to actual
Prediction to creation.
Yeah. It's no longer about, optimizing a guess, like trying to figure out the likely price of a house or classifying whether an image has a cat or a dog in it. That's old news.
Right.
Generative AI is about systems that learn the underlying rules of reality well enough to produce entirely new, coherent content. I mean, we're talking about generating a human-like voice, composing a novel piece of music, or writing sophisticated context-aware text that literally didn't exist a moment before.
And what I find truly fascinating, what really gets me, is how the emergence of these generative models shows how machine learning is just. It's uniquely suited to what some researchers call defeating the monster of complexity.
That phrase is so powerful. It really is, because it perfectly captures the breakthrough.
It does.
Just think about traditional procedural programming for a second. If you wanted a system to recognize, say, 100 different faces, you would have to write this monumental, intricate, just impossibly long list of explicit rules.
Like if the eyebrow angles is X and the distance between the pupils is Y, that kind of thing.
Exactly that. And the skin texture is Z. It goes on and on. And that kind of system, it inevitably breaks down as soon as the complexity starts to rise.
Of course, because the human defining those rules can only account for so much variance. There's always going to be an edge case you didn't think of.
Precisely. And generative AI it sidesteps that impossible task completely. Instead of a human hand-coding millions of lines of rules, the machine learns the complexity directly from the data itself.
So you're saying a deep learning program, which might only be a few hundred lines of code.
A few hundred lines, yeah. That short program can acquire the knowledge needed to handle variances that would have taken literally millions of human-written rules to cover. It's a dramatic simplification of the human effort required to manage just an immense complexity.
Okay, so if machine learning is the big umbrella, the whole field, where exactly does generative AI fit within that established landscape?
Well, generative AI is a very advanced specialization, but it really stands on the shoulders of the two foundational pillars of machine learning.
Okay, what are those?
So first, you've got supervised learning. This is probably the one most people are familiar with. It's learning from labeled data where we already know the answer.
Right, you showed a picture of a cat and you tell it, this is a cat.
Exactly. We use this for classification. Is this a picture of a tree or regression? What's the next number in this sequence? The model is explicitly supervised by the correct answers.
That's the easiest one for me to visualize, for sure. You give it examples and it just learns the mapping between the input and the output.
Exactly. Then the second pillar is unsupervised learning. And here, the data is unlabeled. There are no right answers given. The model has to discover the inherent structure or groupings or representations all on its own.
So what would be an example of that?
A classic example is clustering. Using an algorithm like k-means, which groups similar data points together without ever being told what those groups actually represent. It just identifies the natural organization in the data.
And generative AI, then, is often kind of a hybrid of the two.
It absolutely is. It's a fusion. Generative models frequently use concepts from both. For instance, before a system can generate language, it might use unsupervised methods to learn these really complex semantic representations of words, basically numerical vectors that capture meaning.
And that unsupervised learning part is the foundation.
It's the foundation that empowers the more refined, supervised style generative capabilities that come later. The overarching theme, really, is that these generative algorithms thrive precisely where the problem space, whether that's generating a novel image or composing a paragraph, is just too complex or too intricate to be solved by any traditional set of human-defined rigid rules.
Okay, let's step into the engine room then. If generative AI is the application, deep learning is definitely the fuel. So what are the absolute basic building blocks that allow us to model this unbelievable level of complexity?
At its heart, everything really starts with the neural network. We talk about networks learning by example, and it's a process that's, loosely inspired by the parallel processing in the human brain.
And the most basic unit.
The fundamental conceptual unit, historically, is the perceptron. It's a very, very simple unit that takes inputs, it weights them, sums them all up, and then it makes a simple decision about whether or not to fire.
Okay, so that sounds like a single, simple decision maker. But the transition to deep learning implies we're layering these things. Why is that depth, using multiple hidden layers, so critical for creation?
Because depth is what allows the network to break free from linearity. That's the key. Simple linear models, even if you try to get fancy with polynomial extensions, they are fundamentally restricted.
What do you mean by restricted?
I mean, they can draw a straight line or maybe a simple curve to separate data points,
Yeah.
but they can't capture the true, chaotic, nonlinear functional form that generates real-world data. And that's what we're dealing with, whether the data is language or sound or images.
Real-world data is inherently messy and nonlinear.
Terribly messy. So deep learning systems use multiple hidden layers, one stacked right on top of the other, to let the network learn increasingly abstract and complex representations of the data.
So it's a hierarchy.
A hierarchy of complexity, exactly. The first layer might learn something simple, like edges in an image. The next layer might combine those edges into basic shapes. The layer after that combines those shapes into objects, like an eye or a nose. This hierarchical learning is how they can model those incredibly complex nonlinear relationships that a single layer network just. It simply cannot process effectively.
And key to that nonlinearity is something called the activation function. This is sort of the mathematical switch that determines if a neuron gets excited enough to pass information forward. I know the history here is really interesting. We used to love the sigmoid function, but now it seems like it's all about RealU.
Oh, that evolution is absolutely critical to understanding modern deep learning. The sigmoid function was, very intuitive at first because it squashes any input, no matter how large or small, positive or negative, into a tidy range between 0 and 1.
Which is useful because you could interpret the output as a probability.
Exactly. You could easily see it as a probability. And for a long time, it was the standard bearer. It was what everyone used.
But it created massive practical problems when you started building deep networks, right?
A gigantic problem. A really huge one, particularly related to the mechanics of training the network.
The actual learning process.
The learning process itself. Training a network relies on this algorithm called gradient descent, where we calculate the derivative of the loss function, we call that the gradient, to figure out how to adjust all the weights in the network. The problem is, when inputs to the sigmoid function are very large or very small, the function itself becomes almost flat. It saturates.
Which means the gradient, the derivative, becomes very close to 0.
Exactly. And when the gradient is near 0, it means the necessary updates to the weights are just vanishingly small. This is the infamous vanishing gradient problem.
I've heard of that.
In a network with many, many layers, those tiny gradients get multiplied together as they're passed backward through the network, from the output layer to the input layer. And this essentially causes the updates in the earliest layers, the ones closest to the raw input, to completely stop. They just grind to a halt.
So the deepest part of the network, the part that's supposed to be learning the most fundamental, basic features, it just freezes up. It can't learn.
It paralyzes the network. It was a huge bottleneck. And this is where RealU, the rectified linear unit, was a total game changer because it largely solves this problem.
How does it work?
It's surprisingly simple. For any positive input, the output is just the input itself. And for any negative input, the output is 0. That's it. But crucially, when the input is positive, the derivative, the gradient, is exactly 1.
A gradient of 1. That sounds perfect for optimization.
It's magnificent. It's what you want. It allows the gradients to flow backward through the network completely undiminished, at least in that positive region. RealU is also simpler to compute, it's faster, and most importantly, it mitigated the vanishing gradient problem enough that we could finally start training networks with dozens, even hundreds of layers effectively. RealU is really the feature that made deep learning practical and scalable.
Okay, so the structure and the activation function set the stage. But the actual learning, as you said, is this massive iterative optimization process. Can you tell us more about the mechanics of that? How does the network actually learn?
Right, so training is pure optimization, nothing more, nothing less. We have a cost function or a loss function, something like mean squared error for regression tasks or cross entropy for classification. And this function just measures how wrong the model is.
So the goal is to get that wrongness number as low as possible.
To get it as close to 0 as you can. Our goal is to iteratively minimize that loss function until we find the optimal values for all the parameters, the weights, and the biases of the network. And we're talking about millions, or in the case of large generative models, even billions of parameters.
And with billions of parameters, You can't just use standard calculus to find the one perfect solution,
Yeah.
right? There's no single equation you can solve.
Impossible. It's computationally intractable. That's why we have to rely on these iterative approximation techniques, and the main one is gradient descent.
How does that work in practice?
We take a small sample of data, a mini batch, we feed it through the network, calculate the loss, and then we use the gradient to determine the direction in this high-dimensional weight space that will reduce the loss most quickly. Then we just take a small step in that direction.
And you just repeat that over and over.
Over and over, batch after batch, through many cycles, which we call epochs, until the loss stops improving.
And the size of that step you take is absolutely critical. That's the learning rate.
Correct. The learning rate, which you'll often see denoted by the Greek letter alpha or eta, determines the size of the adjustment we make to the weights. If it's too large, we might overshoot the minimum loss, point like stepping clear over the bottom of a valley. If it's too small, training takes forever, and you might get stuck and never reach the minimum in a reasonable amount of time.
So how do you find the right one?
Well, modern implementations, like the Atom Optimizer, are incredibly efficient because they don't just use a single fixed step size. They dynamically adjust the learning rate for each individual parameter based on historical gradients, which accelerates convergence dramatically.
So even with ReLU helping with the vanishing gradient, I know that deep networks still had this profound instability issue, especially early in the training process. What was that problem, and what was the engineering solution that basically became indispensable?
The problem was a phenomenon called internal covariate shift. It's a bit of a mouthful.
Internal covariate shift.
Yeah. So even if the final output of the network was stable, the internal distributions of features, so the outputs of all the hidden layers, were constantly shifting wildly as the weights of the previous layers changed during training.
Oh, I see. So layer 5 is trying to learn a stable pattern, but the input it's receiving from layer 4 is constantly changing its statistical properties, its mean, its variance.
Exactly. It's like trying to build a castle on shifting sand. It's an impossible task. This constant fluctuation meant we had to use an incredibly tiny learning rate just to prevent the whole system from numerically exploding, which, again, made training miserably slow. And this is the stability issue that batch normalization, or batch norm, was invented to solve.
Okay, batch normalization. So how does standardizing features across a mini batch of data fix this shifting sand problem?
What batch norm does is it standardizes the inputs to a layer across each mini batch. For a given batch of data, it calculates the mean and the standard deviation of that layer's inputs, and then it normalizes them to have a mean of 0 and a standard deviation of 1.
So it forces a consistent statistical profile on the inputs to every layer.
Exactly. It forces consistency. And by stabilizing the distribution of inputs to a layer, we can suddenly use much higher learning rates. This drastically speeds up convergence, and it also reduces the model's sensitivity to how the parameters were initially set.
That makes a lot of sense for stability. But I have a question. If you force every single input feature to have a mean of 0 and a variance of 1, doesn't that restrict the model's representational power? You might be forcing the system to ignore some beneficial, natural shift or spread in the data that's actually important.
That's a brilliant question, and it's a crucial point. If we only standardize, we would absolutely be in danger of removing important information. The designers of batch norm knew this.
So what's the fix?
To prevent this, batch norm introduces 2 learnable parameters after the normalization step. A learnable scaling factor, we can call it gamma, and a learnable shift factor, which we can call beta.
Aha. So these aren't fixed hyperparameters that the human sets. They're actual parameters that the network learns during training, just like the weights.
Precisely. They allow the network to optimally rescale and shift the normalized features back to a more appropriate distribution if it needs to. The network essentially learns the best way to normalize itself for maximum performance.
So it can learn to undo the normalization if that's what's best.
It can. If the optimal distribution for a given layer happens to be a 0 mean and unit variance, then gamma will learn to be 1 and beta will learn to be 0. But if the optimal distribution requires a different mean and spread, the network learns that too. This maintains the full expressive power of the network while still getting all the speed and stability benefits of the standardization.
This sounds like a really profound interaction between the machine's automated learning and the very intentional design choices made by the human engineer. And those design choices, the settings we make before the learning begins, those are the hyperparameters, right?
They are the designer's fingerprint on the model. And the model's ultimate performance is acutely, incredibly sensitive to its hyperparameters. The number of layers, the size of those layers, the choice of optimizer, and, as we just discussed, the learning rate. These aren't learned from the data. They are set by us, the engineers.
And the process of tuning those hyperparameters, I imagine, must be done very, very carefully to avoid contaminating the model's final evaluation.
Oh, rigorously so. You cannot use your main training data to tune hyperparameters. If you do, the model will simply learn the settings that work best for that specific set of data, which leads to inflated, overly optimistic performance metrics.
So what do you use?
You must use a separate validation dataset. This validation set acts as a proxy for the unseen test data. We iterate on different hyperparameter settings until the validation loss is minimized, and only then, when we've locked in our choices, do we test the model on the final, pristine test set that it has never, ever seen before.
But tuning these massive deep networks must be incredibly expensive. If I have, say, 10 different hyperparameters and each has 10 possible settings, that's 10 billion combinations I might have to try. Brute force methods like a grid search are just totally infeasible for models that take days or weeks to train once.
That's the bottleneck. You've hit it exactly. Simple grid search or random search just explores the hyperparameter space blindly. It's incredibly inefficient. This is where more advanced methods like Bayesian optimization come in.
Bayesian optimization. Okay, that sounds complex.
Yeah.
How does it manage to be smarter about where to look next for good settings?
It's sophisticated, but the core idea is really elegant. It treats the hyperparameter optimization problem as a statistical modeling problem in itself. Instead of testing every single combination, it builds a probabilistic model, what we call a surrogate model of the objective function.
The objective function being the model's performance.
Right, so the surrogate model estimates what the performance will be for hyperparameter settings that haven't even been tested yet.
So it's essentially predicting which combination of learning rate, layer size, and so on will yield the best result before it spends all the time and compute resources to actually train the full, expensive, deep learning model with those settings.
Exactly. It uses Bayes' theorem to update its belief about the landscape of the objective function after each new experiment it runs. This allows it to intelligently balance exploration trying settings it knows very little about and exploitation refining settings that have already shown promise. In applied ML, especially with these huge deep learning models where evaluating the objective function is just extremely costly, Bayesian optimization can save staggering amounts of compute time, energy, and money compared to exhaustive searches.
Let's shift gears now from the foundational optimization mechanics to the architectures themselves. When we start talking about generating human-like language, we're dealing with sequential data, where the order of things is everything. So how did machine learning first tackle this challenge of generating coherent sequences?
Well, the initial specialized architecture for this was the recurrent neural network, or the RNN. RNNs are designed to handle sequences by maintaining an internal state, a kind of memory, that gets updated at each step of the sequence. It uses its own output from the previous time step as an input for the current one, which is what makes it recurrent.
But the simple RNNs had a really crippling flaw when it came to reading a long document or a long conversation, didn't they?
They did. They suffered severely from the vanishing gradient problem, but this time in the time dimension, not just the depth dimension. So if you were analyzing a sentence that was 100 words long, the network would essentially forget the context that was set by the first few words by the time it reached the end.
They couldn't manage long-term dependencies.
Exactly. They had very short memories. If the subject of a sentence was introduced early in a long paragraph and that determined the correct verb tense much, much later, the simple RNN would often fail. It would forget the subject.
And this failure, this lack of memory, led to the invention of the long short-term memory networks, or LSTMs. This is where the complexity really ramps up with this idea of gates.
LSTMs are absolutely fascinating because they introduce this elaborate internal mechanism specifically designed to combat that forgetting. You can think of the internal memory structure of an LSTM as a main river of information. We call it the cell state, and this river, the cell state, runs relatively straight through the entire sequence from beginning to end.
Okay, a river of information.
Yeah.
And the gates are what control that river.
They are the computational floodgates, exactly. An LSTM has three of them. First, you have the forget gate. Its job is to decide what information that's currently in the river, in the cell state, is no longer relevant and should be tossed out.
Okay, so it learns what to forget.
It learns what to forget. Then you have the input gate, which determines what new relevant information from the current word in the sequence should be allowed to enter the river.
And the final one determines what the network actually says or does at that moment.
Right, that's the output gate. It regulates how much of the information that's currently in the cell state is exposed to the next level of the network or is used to generate the current output word. By having this explicit trainable control over what is remembered, what is updated, and what is exposed, LSTMs can maintain coherence and manage dependencies across hundreds or even thousands of words in a way that simple RNNs never ever could.
And a prime application for this kind of sophisticated sequence management is neural machine translation, or NMT. We're talking about true end-to-end generative systems here.
NMT absolutely revolutionized the field of translation. Prior systems were often these clunky rule-based or phrase-based systems, but modern NMT systems are true end-to-end generative models. They take an entire complex sentence in a source language, they encode all of that complexity into a single fixed-size vector, and then they decode that vector into the target language.
So the system learns the entire mapping between languages directly.
It learns the massive nonlinear mapping between languages directly without relying on any intermediate human-defined linguistic features or rules.
But if you have a very long, complex sentence, cramming all of its meaning into one single vector sounds like it could be a severe information bottleneck. How did the machine learn to prioritize which source words matter most when it's translating a specific part of the sentence?
That bottleneck was the next major hurdle, you're right. And it was solved by the introduction of the attention mechanism. Attention. It allows the decoder, that's the part generating the output, to look back at all parts of the encoded source text, not just the final summary vector. So when the decoder is about to generate, say, the 10th word in the output sequence, it calculates a set of weights that tell it which of the source words are most relevant to generating that specific output word.
Okay, so if I'm translating the sentence, the big red dog quickly chased the ball, and the model gets to the word chased in the translation, the attention mechanism might heavily focus its weight on the source words for dog and chased, and maybe less on big or red.
Exactly right. It selectively focuses its computational resources, which vastly improves the quality and coherence of the translation, especially for very long and complex sentences.
Now let's get into a technical nuance here that's really critical for training these attention-based generative models. Masked attention. Why is this masking technique so vital for the generation process?
It's absolutely vital. It's a requirement to ensure that the training environment perfectly mimics the real-world deployment environment.
What do you mean by that?
Well, imagine we're training the model to generate a sentence. During training, the model actually has access to the entire correct target sentence all at once. If we didn't mask it, the model could effectively cheat by looking ahead at the word it's supposed to generate next.
Which would make the training task trivial, but then the model would be useless in the real world.
Precisely. In deployment, when the model generates word I, it only knows the words that it has generated previously, so words 1 through I1. It can't see the future. Masked attention is a procedure that we apply inside the decoder during training that prevents the model from attending to or looking at any words in the target sequence that occur after its current position.
So it enforces causality.
It enforces that strict causal constraint of sequential generation. This guarantees consistency between how the model is optimized during training and how it actually functions in the real world.
This entire sophisticated language architecture, though, it relies on one really critical precondition. The machine needs a way to numerically represent words in a way that captures their meaning. And this brings us back to unsupervised learning and the classic technique, word-to-vec.
Word2Vec is a perfect illustration of unsupervised learning creating the foundation for generation. It's a family of models that creates these dense numerical vectors we call word embeddings. And these vectors are specifically designed to capture semantic and syntactic context, converting abstract words into a continuous mathematical space.
So how does it learn the meaning of a word without ever being told what it is?
It leverages a linguistic concept called the distributional hypothesis.
Okay.
Which is really just a fancy way of saying that words that appear in similar contexts tend to have similar meanings. Word2Vec doesn't care what the word king means to a human. It just looks at the words surrounding it in a massive text corpus. If king and queen both frequently appear next to similar sets of other words like ruler, throne, palace, their resulting numerical embeddings will be mathematically close to each other in the vector space.
And the magic is that once they're vectors, you can actually perform arithmetic on them. I always love the classic example of this.
The famous analogy, right? The vector for king minus the vector for man plus the vector for woman mathematically results in a vector that is very, very close to the vector for queen. This was a groundbreaking result because it demonstrated that unsupervised learning could capture these subtle semantic relationships and analogies, providing the rich, meaningful input that is required for sophisticated generative text models.
Okay, let's move from language to the creation of synthetic data. We need to talk about the two major architectural categories for this: autoencoders and generative adversarial networks, or GANs. Let's start with the autoencoder.
An autoencoder is structurally quite simple, but it's conceptually very powerful. It's a deep neural network that's designed with two main halves: an encoder and a decoder.
Encoder and decoder.
The encoder's job is to take the input, let's say it's an image, and compress it down into a much smaller, lower dimensional representation. We often call this the bottleneck or the latent code. Then the decoder's job is to take that compressed code and reconstruct the original image as faithfully as it possibly can.
So in order to do that successfully, it's forced to learn only the most essential features of the image to perform the reconstruction.
Exactly. If you can successfully compress and then reconstruct an image, you know the model has learned the essential abstractions and it's discarded the random noise. Autoencoders are incredibly useful for dimensionality reduction, for feature extraction, and especially for denoising.
How does it work for denoising?
You can feed it a noisy, corrupted image. The bottleneck forces it to learn the core, clean patterns underneath, and then the decoder reconstructs the clean pattern while ignoring the random noise it saw in the input.
And the variational autoencoder, the VAE, is what pushed this idea into the truly generative domain.
Right. The VAE introduced a probabilistic framework to the whole process. Traditional autoencoders don't guarantee that the latent space, that bottleneck area, is smooth or continuous. So if you try to sample a point in that space that's between two known codes, you might just get meaningless gibberish as an output.
So VAEs fix that.
VAEs enforce structure on that latent space by balancing two competing goals in their loss function.
What are those two goals?
Okay, so first, it wants to maximize the reconstruction likelihood, just like a regular autoencoder, making sure the output looks like the input. But second, it tries to minimize the information loss, which is quantified using a measure called KL divergence between the distribution of the compressed latent space and a simple known prior distribution, which is usually a standard normal distribution.
So it forces the latent space to be well-behaved.
Exactly. It ensures the latent space is smooth and continuous, which means you can now sample any random point in that space and get a meaningful, novel generation out. That's what makes VAEs true generative models.
But for generating synthetic content that achieves, true photorealism, it seems like nothing beats the generative adversarial network, the GAN. This architecture is built on a battle, right?
It is the ultimate architecture of competition. The fundamental concept is an adversarial game between two separate deep neural networks, the generator and the discriminator. The best analogy is to imagine a forger and an art critic who are constantly challenging each other.
The generator is the forger.
The generator is the forger, yes. Its one and only goal is to create synthetic content, say an image of a face that doesn't exist, that is realistic enough to fool the critic. The discriminator is the art critic. Its job is to look at an image and correctly classify whether it is real, meaning from the training data, or fake, meaning it came from the generator.
And through this competition, they both improve each other.
The beauty of the GAN is that simultaneous improvement. As the generator gets better at creating highly convincing fakes, the discriminator is forced to become more and more discerning to correctly spot them. Conversely, as the discriminator gets better, the generator is forced to evolve its strategies to create even more realistic content. This continuous adversarial training process drives both networks to a performance equilibrium where the generator is producing incredibly realistic synthetic data.
When GANs are used for high-resolution images, I think they're called deep convolutional GANs or DC GANs, the generator has to take that tiny latent code and somehow inflate it into a full high-resolution image. That must involve some very specialized operations.
It does. It requires upsampling, and the specific operation used is called transposed convolution. You might also hear it called deconvolution or fractional stride convolution, but those are less intuitive names.
So what is it doing?
Well, in a traditional image discriminator, you use things like pooling or strident convolutions to downsample the image to reduce its size while preserving key features.
Okay, so the transpose convolution must just reverse that process.
It essentially reverses the geometric transformation. The generator needs to take a smaller feature map and expand it to produce a large, high-resolution output image. Transposed convolution achieves this by applying a convolution-like operation that results in a feature map that is larger than the input. It's a precise, learnable way to perform upsampling while preserving the structure and features learned from the latent code, which is why it's absolutely critical for generating realistic, high-fidelity images.
The sheer complexity of these models, training a GAN or a massive transformer model requires huge data sets and immense computational power. It seems like operationalizing them is a task that's really only for advanced managed platforms these days.
Oh, managed services are no longer optional. For industrial-scale AI, they're essential. Services like Amazon SageMaker take on the massive operational burden. They abstract away all the complexity of provisioning and managing the underlying infrastructure, which allows data scientists to focus purely on the modeling and the data, which is what they're good at.
So the data scientist isn't spending half their time just setting up distributed training clusters and managing servers.
Exactly. They are provided a secure, scalable workbench, often it's a managed Jupyter Notebook environment, to perform their feature engineering, run massive distributed training jobs, and then manage the resulting models. This acceleration of the ML lifecycle is perhaps the single greatest productivity boost in modern AI development.
And once that model, the trained artifact, is ready, and it's usually stored securely in cloud storage, how do we actually turn it into a live service that applications can call 24/7?
SageMaker handles fully managed model hosting for you. It takes that trained model artifact and it deploys it onto compute instances, automatically generating a private, secure HTTPS endpoint. Applications then simply call this API endpoint for real-time inference or prediction.
And I know a key capability here is something called production variance. What kind of flexibility does that give developers?
It allows for some really sophisticated testing and optimization in a live environment. You can deploy two versions of a model at the same time. Let's call them Model A and Model B. And you can direct, say, 90% of your live traffic to the established, trusted Model A and just 10% to the new experimental Model B.
So you can do live A/B testing.
Live A/B testing. You can even run Model A on cheaper, cost-effective CPUs and run Model B on high-performance GPUs to compare them. This traffic splitting allows for safe testing of new generative models without ever interrupting the main production service, optimizing both for performance and for cost.
Deployment, though, as you said, is only the beginning. The operational excellence has to continue through constant monitoring. What happens when the world changes outside the lab?
And it always does. That is where continuous monitoring services like Model Monitor become absolutely indispensable. Generative models, especially the ones trained on dynamic data like language or market trends, are highly susceptible to a problem we call data drift.
Data drift.
Yeah. So if the pattern of the incoming live data suddenly changes, for example, if a model was trained on formal news text and it suddenly starts receiving high volumes of informal social media chat, its performance is going to degrade, and probably significantly.
So Model Monitor is checking the quality of the incoming data itself, not just the model's output predictions.
It checks both. It continuously monitors model quality metrics and data statistics in real time, and it compares them against established baselines from the training data. If a deviation is detected, if the distribution of incoming features shifts too far from what the model was trained on, Model Monitor issues an alert. This proactive detection ensures that the model's reliability is maintained and prevents that kind of silent performance degradation that could lead to financial losses or a really poor customer experience.
Beyond building these custom models from scratch, cloud platforms now offer a lot of ready-to-use generative and related services. Could you give us a couple of examples of these off-the-shelf tools that are built on these deep learning principles we've been discussing?
Sure. A classic generative example is Amazon Polly, which is a text-to-speech, or TTS conversion service. It utilizes very advanced deep learning to generate incredibly lifelike, nuanced voices across dozens of languages. It takes text input, which can be just plain text, or, for more control, highly structured input using something called speech synthesis markup language, or SSML.
And SSML allows you to have fine-grained control over the nuances of the voice, right?
Exactly. With SSML, you can specify details like pauses, pronunciation, the volume, and even the emotional tone of the voice. This ensures the output is not just intelligible, but truly natural and context appropriate. It is a very powerful commercial application of generative synthesis.
And the inverse operation, taking sound and turning it back into text.
That would be Amazon Transcribe. This service is designed to handle high-volume, often multilingual, speech-to-text transcription. It can operate in a real-time streaming mode, which is crucial for things like live customer service interactions, or it can work in a batch mode for processing massive archives of recorded audio data, like market research interviews or corporate compliance logs. It's an essential tool for converting unstructured audio into structured, searchable data.
Finally, we should talk about deployment flexibility. Not all generative applications can or should run in the cloud. Sometimes latency demands or privacy concerns require local deployment.
Absolutely. Low latency use cases are a big one. Think about real-time computer vision on a factory floor or immediate voice activation on a consumer device. You just can't tolerate the network lag that's associated with calling a cloud endpoint for every single inference. The solution here is the edge deployment pipeline.
How is that achieved with these complex, huge models?
Services like AWS IoT Greengrass and SageMaker Edge Manager allow developers to train a really robust, large model in the cloud, leveraging massive resources, but then compile and deploy a lightweight, optimized version of that same model directly onto edge devices.
With small hardware like cameras or local servers or embedded chips?
Exactly. This enables complex, low-latency generative tasks like on-device natural language processing or visual inspection to run entirely outside the data center firewall.
Okay, now let's address the really crucial topic of trust and evaluation. The scientific principle is pretty clear. A model's patterns have to be verified on new, unseen data, or you should just never trust it. What is the fundamental failure mode we're trying to avoid here?
The single biggest failure mode is overfitting. If a model performs perfectly on the data it was trained on, but then its performance completely collapses when it faces new data, it means it didn't learn the generalized, underlying patterns of the data-generating process. Instead, all it did was memorize the random noise or the specific idiosyncrasies of that one training set. We need a model that can generalize, not just one that can recite history.
And managing that ability to generalize requires constantly wrestling with the bias-variance trade-off.
This trade-off is absolutely central to robust machine learning. Bias refers to the simplifying assumptions a model makes about the functional form. So high bias means the model is too simple and it's missing the true patterns. Variance refers to the model's sensitivity to the noise in the training data. High variance means the model is too complex and it ends up fitting the noise rather than the signal.
So generative models, being these incredibly complex, deep architectures, where do they tend to fall on that spectrum?
They inherently trend toward low bias. They are nonlinear enough to capture virtually any relationship you can imagine. But this complexity often leads to high variance. They are very prone to fitting noise and failing to generalize. The whole goal of the data scientist is to find that elusive sweet spot right in the middle to achieve enough complexity to model the real patterns. That's low bias, but not so much that it memorizes all the noise. That's low variance. And techniques like cross-validation and regularization are the critical tools we use in that management process.
There's a particularly dangerous form of overfitting that the research details, and it's especially relevant in fields like algorithmic trading, where models are generating optimized strategies. This is backtest overfitting. Why is this so insidious, especially in time series data?
Backtest overfitting is a really nasty selection bias problem. It happens when a researcher repeatedly tests many different strategies or model configurations against the same set of historical data until, just by chance, one happens to look profitable. Essentially, what you're doing is finding a model that is perfectly optimized to monetize the random noise that happened to occur in the past, but which has absolutely no predictive power for the future.
So if the model is generating a brand new strategy, how do we know if it's based on a real signal or if it's just capitalizing on historical randomness?
We often don't, which is why methodological rigor is everything in this field. And the danger is compounded by a very specific issue in time series analysis. Data leakage that can happen right near the boundaries between the training and the test sets.
Can you walk us through a detailed example of that boundary leakage? Because that seems really subtle.
Certainly, it's very subtle but critical. Imagine you're building a financial model where the target variable is a prediction of a stock's price movement 10 days into the future. Your training data ends on, let's say, day 100, and your test data starts on day 101.
Right.
Now, let's say you calculate an indicator, like a 50-day moving average, for the training cases right near that boundary. For instance, a case calculated on day 99.
Day 99 is clearly in the training set. No problem there.
Right, but what is the target variable for day 99? It's the price movement 10 days later, which is on day 109. And days 101 through 109 are explicitly part of your test set.
Oh, I see.
Therefore, information about the future information that is contained in the target variable of a training case has leaked into the data space of the test set.
So the model inadvertently learns something about the test set's behavior while it's still technically training on what you think is past data.
Absolutely. The training process is using information that is temporally dependent on the test data. And this leakage leads to these artificially optimistic, wonderful-looking performance metrics when you finally evaluate the model. The reported high Shark ratio or high accuracy on the test set is a lie, because the test set was not truly unseen. This undermining of statistical soundness is why proper techniques like setting a clean temporal gap between your training and testing periods or using rigorous walk-forward validation are absolutely essential for evaluating any generative or predictive model that touches time series data.
So as we wrap up, it seems clear that our deep dives today confirms that generative AI really is a realization of machine learning's highest potential. It's the automation of knowledge and content creation, tackling problems that were just fundamentally intractable to traditional coding.
That's right. We've detailed the entire pipeline, from the really microscopic level of optimization and stability, where things like ReLU and batch normalization were essential to even handle deep complexity, all the way up to the architectural solutions like LSTMs and masked attention that allow machines to compose language intelligently.
And the infrastructure surrounding these systems is equally complex, geared entirely toward managing and controlling their immense power. This covers everything from careful data preparation, dealing with missing values and standardization, to the industrial-scale deployment flexibility that lets models run on massive cloud clusters or tiny edge devices, all while being continuously monitored for performance degradation and data drift.
And this technological maturity means the capabilities we've been discussing, they're no longer academic curiosities. They are scalable, global production tools right now.
Which brings us to our final moment of critical reflection. We know that learned models already control vast, important segments of human decision-making. They deeply influence fields from high-speed finance to law enforcement. As these generative AI systems evolve even further, gaining the sophistication to, say, autonomously program themselves, create entirely new content, and invent new knowledge structures, we really face a critical challenge regarding our human priorities. So here's the thought I want to leave everyone with. If the capacity to innovate and create is rapidly shifting from human hands to machine architectures, if the next great novel or the next life-saving pharmaceutical compound is generated entirely by an AI, should the primary focus of researchers shift entirely away from the simple pursuit of better prediction performance? Should the goal stop being just about achieving a higher accuracy score or a lower loss metric and instead focus entirely on designing systems with better built-in ethical and control parameters? What does the architecture of a truly responsible AI look like when its core output is creation, not just classification? That, I think, is the defining question we must answer as this new era unfolds.